All right, welcome back. We have a record number of people in class right now. This is amazing.
11 is?
Oh god, yeah. We're normally at like 5 when class starts. And if we're lucky, we get to like 10 or 11 by the end of the class.
Maybe you ought to think about there's probably a consequence of recording all your lectures so nicely.
Yeah, but those are useful, so I don't really want to stop doing that.
Yeah,
but
useful.
The recordings aren't so good at like answering questions when people ask questions. All right. I hope everybody had a good weekend, and we have 2 weeks of the quarter left, and then we're done. So, you know, wherever you are in your classes, the end is coming soon. Which, when I was in school, that was always a good feeling. It usually kicked in like about 3 hours before the final exam. I was like, well, it's gonna be over in like 5 hours. So, there's like comfort in that sometimes. But we're in good shape in this course right now. We're coming up to the end of the main material. Some of this material will get expanded on in 223. We're going to talk a little about sorts, and some of that may get moved over into spring. Graph theory may get pushed into spring, and so on. But my plan for today is to start off with PA5. PA5 has been up for almost a week now, so I want to make sure everybody's like making good progress on that. Go over any questions about that first, get that out of the way, and then I'll go back and talk a little bit about PA4, the binary tree assignment that that's been graded and comments posted, and then after that I want to move on to some other aspects of a dynamic programming, which is PA5. We talked about the knapsack problem. But I want to go ahead and dig into some other examples of problems that work well with dynamic programming. So we'll do that, and then we'll move on to probably talking about balancing binary trees, and then sorting and searching. So that's probably our plan for the rest of the week. So any questions before we start?
The SLP thing is tomorrow at 3?
The SLP thing is next Tuesday, 3 o'clock to 5 o'clock.
Oh, next Tuesday.
Yeah.
Oh, that's awesome. I think I interrupted someone, sorry.
Oh yeah, sorry. So the way that max value works, we're going to have to save like a static variable that points to the array, correct?
You probably don't want a static. You don't need globals in here, and so on. We'll be able to pass these things back from the function, and that's really the right way to deal with situations where we think we want a global. The proper way to do that is usually to pass things to and from functions. We didn't do that earlier because we were trying to kind of simplify the hash assignment, but for this one, yeah, we'll just go ahead and pass these around as structures. And I'm gonna go through a detailed example of working out the maxval problem to kind of illustrate how you keep track of that inventory information along with keeping track of the maxval itself. I'm printing up some worksheets I'm going to use here. Let's see, do we have to be there the full 3 to 5 o'clock block? That would conflict with one of my classes. If you have a class conflict, then come for the part of the presentation that you can and leave when you have to for class, so you're not required to skip another class to come to this. And looks like the majority of people uploaded their SLP posters. If you completely forgot about it and have not uploaded your SLP, please, please, please do that like right away. Like, stop listening to what I'm saying and just push your poster out to Canvas. You can't use slip days on it, but if you get it in, like, you know, in the next hour or so, I'll still be able to go ahead and count that. And the posters I've looked at so far, they look good. And the presentation, again, you know, it's pretty low key. It's really just, it's going to be a Zoom session with different breakout rooms, and you'll be in a room and basically just, you know, 5-minute, 10-minute presentation. Just talk about what you've done, where you are with the project, the basic idea of the project. If you want to use your poster, you can use that. You can screen share whatever you like. If you have, you know, a working version of your project, some code or, you know, a gadget or something, you can certainly go ahead and share that. And it's really just kind of, you know, getting some practice at talking to whoever might be interested in hearing about what you've been doing for this project. PA4 I'm going to come back to after PA5.
I have a question.
Yeah.
So I think we talked about this last week, but can you remind me about like what's the algorithm or what's the strategy of you making a recursive function for PA5? Like how would you be able to store already calculated values? Is it like an array of integers kind of idea, or
so storing the already calculated values, that's the dynamic programming piece. There's no recursion in that. That's something that happens in the beginning of your recursive function. You check to see if you've done this calculation before, and if you have, you just read the saved value from memory and return. What that cache should look like is probably going to be an array of structures, because you're going to need to store the maximum value for a certain capacity, but also the inventory of items that get you that maximum value. So if you look at, you know, element 5 in your array, it says if I have 5 pounds capacity, I can get a maximum value of 17, which I get by doing 2 of item 1 and 1 of item 4. So all that information needs to be saved in your cache. Make yourself a structure that contains, you know, a maxval and inventory of items. The inventory can be just a simple array. If you have 128 items, it's an array of 128 elements, and each entry tells you how many of each item you take to get that maximum value. And again, we'll go through a detailed example of that in a bit to sort of work out those details, particularly for the inventory piece, because the inventory piece is kind of an extra layer of trickiness. All right, so let me start with PA5. Like I say, this has been posted for about a week now. I think I posted it last Wednesday. Pretty much what we already talked about in class last week. So PA5, you're going to implement the... sorry?
When's this due? Sorry.
This is due on Tuesday, a week from tomorrow. And I moved that back one day. It was originally due a week from today. But I decided to move it back one extra day, so it's due a week from tomorrow. 8 a.m. as usual. So you're going to implement the unlimited integer knapsack problem. So this is a problem where you're allowed to take only whole amounts of items from the inventory. So you can't take half a mouse or a quarter of a cell phone. You have to take whole numbers of these, and you have an unlimited supply of these available to choose from. And so your main program has to be called knapsack, and it takes exactly 2 arguments. The first argument is the capacity of your bag. The second argument is a file name that contains an inventory like this. So the inventory consists of triples with a name, which contains no spaces, a value, and a weight. And these are integers. So this says a mouse is worth 5 and costs 1, a cell phone is worth 100 and costs 2, and so on and so forth. And then your goal is for this capacity figure out, you know, if I pack certain numbers of these items in, what's the highest value that I can get by packing this in such that my total weight does not exceed 100, and what's the solution, what's the combination of these items that I should use to get that maximum value. So you want to know the max val and you want to know the inventory. And so this all boils down to writing this maxval function that we talked about last week. We're going to work through it again today with a specific example. Basically, maxval for capacity x is the largest of these calculations. Value of your first item plus maxval of x minus the weight of the first item. Value of the second item plus maxval of x minus the weight of the second item, and so on. And you iterate over all the items that can possibly fit in your bag with capacity x, so any item that weighs x or less, and you calculate each of these, and whatever gives you the maximum value, that's a maximum solution. Alright, as you do this, you keep track of the inventory. We're going to go through that. You have to use dynamic programming. If you don't, I will run test cases that will take forever to finish. So dynamic programming, in the beginning of your maxval function, see if you've already called maxval with this number. If you have, just return the value you calculated before. If not, do all of the recursion, calculate all of these values, find the largest. Before you return, save it in your cache, so that the next time you try to calculate maxval on the same capacity, you won't have to do all the work again. Alright, when you run your program, it should do something like this. It should print out a copy of the inventory file, so the weight, value, and name of each item. Reiterate what the bag's capacity is, that's just the argument that was given, and then print out the maximum value you can get from that bag and the number of each item that gives you that maximum value. Alright, there's a sample executable, temp knapsack, and a sample database file, temp knapsack.data. Feel free to use those and compare the results against your code, but try some other problems also. Right? Make sure your code works if none of your items fit in your bag. Make sure your code works if you have 50 items to choose from. And you can run this sample executable against your executable. Make sure you're getting the right capacity. Make sure your inventory adds up to the capacity, and so on.
Another question?
Yeah.
So does the knapsack data just have a list of items with the corresponding weight and values, or is it just the amount the phone, tablet, laptop?
So it looks like this. There's a name, there's a value, there's a weight.
Okay, so it's just like kind of like similar to the license plate numbers.
Similar to the license plate file, yeah. So 3 things on each line: a name, a value, and a weight. And
Okay.
these are guaranteed to be integers, and this will be a name that does not contain any spaces. So you can read this with a %s, read these with %d.
Do we need to check if there's any errors, like
Yeah, you
if
should.
I don't?
You should make sure that it parses as an integer and all of that usual stuff. I'm not going to deliberately try to trip your program up like that, but put those checks in anyway. So error checking, make sure you handle error conditions, too few or too many arguments, invalid arguments to the program, missing or invalid item file. Okay, you do have to check for invalid item file. So yeah, I might check that. I probably won't, but I might. And so on. Simplifying assumptions, maximum of 128 items in the item file. Why is that important? Because your memory cache is going to be an array that stores the results of maxval for different capacities. Well, if your maximum capacity is 1024, you don't need to be able to store a value larger than 1024. So your memory cache can be an array of 1025 somethings, some kind of structure. 128 items means that you can store what you read in from your file in static arrays. You can declare your item array to be 128, and you don't have to worry about dynamic memory allocation. Name of each item, no more than 32 characters, so you can make those character bracket 33, and you don't have to do dynamic memory. And there's no spaces, so you don't have to worry about weird parsing situations. So no mallocs anywhere in this, right? If you need to do them, you can do them, but you should not need to do any mallocs. You should not need to do any freeze. There should be no memory leaks or memory issues associated with that because of these simplifying assumptions. And then your upload is just pa5.tar to Canvas by the due date. Grading, super straightforward. No upload, no points. That's the usual. Any compile errors, 50 points off. Any compile warnings, 10 points off. If your program's seg faults, you lose half the points. So make sure you don't get seg faults. If it does not come up with any solution, you lose 50 points. If it comes up with a solution but it's not the optimal solution, you lose 30. If it doesn't run in a short amount of time, meaning you didn't implement dynamic programming correctly, so I try to run this on 500 items and it's taking 10 minutes and it hasn't given me an answer, that's a deduction. And if the inventory that's supposed to get you the maximum value is not correct, that's 15 points. I mentioned on Canvas also make sure you include a make file. That's not in here, but you have to include a make file as well, so that if I say make, it'll go ahead and build the executable. If I say make clean, it'll get rid of the pieces that were made.
How many points off if we don't have a make file?
I don't know if I mentioned that in Canvas or not, did I? Probably 10 points. But are you planning to not have a make file?
No.
Okay.
No. I was just asking just us.
Okay.
I think it's because, like, PA4, I've seen multiple people having problems with the make file for some reason.
PA4 actually reduced the make file from 10 points to 5 points because so many people were having problems with it. But make file, you should be able to say make. It should compile everything, build an executable. If you say make again, it should say everything is up to date. If you change a file and say make, it should recompile everything that needs to be recompiled. If you say make clean, it should get rid of everything that's been made, so that if you say make again, it recompiles everything. That's like the constant requirement for make files. And if you say make twice in a row, the second time should not do anything. The first time might not do anything if everything's up to date. But the second time should say everything's up to date. The idea of the make file is when you're developing your program, you don't have to worry about, what do I compile now that I've changed functions or main or main.h or something. You just say make, right? And so my question about, are you planning to not include a make file was really geared towards, a make file helps you when you're developing your project. It's one less thing to worry about. Going back and trying to recall the GCC command and remember to put in -lm if you're doing something with math and so on. Just say make enter, and once you get in that habit, right, you'll never think about GCC again. You'll never think about -o, or you'll never clobber your executable file because you said -o main.c or things like that. You edit your code, you come out of the editor, you say make enter, and you're ready to run and start debugging. And so, particularly on larger projects, we want our make files to be efficient. We don't want to just recompile everything or relink everything every time you say make. So that's what we're shooting for with the make files. And on future projects, when you're working in groups, I guarantee your team members will love you if you have, good make files. And they'll probably, write songs about you if you don't. Let's see, compiling with debugging symbols. Yep, exactly, just throw in a -g anywhere that you want except between the -o and the something. So you could put it right after GCC, you could put it at the end, it can go anywhere you want.
Okay, because I've been putting that in my make file.
Mm-hmm.
Whenever I try and run GDB on it, it says there's no debugging symbols.
But make sure that you put it on every GCC.
Yeah, I made that same mistake.
So, okay, so what I'm seeing here is GCC-G-O something.g and then a bunch of .os. So you also need to have it when you say GCC-C main.c and GCC-C functions.c. And that's actually where the debugging symbols come from, is from the source code. And by the time it gets compiled to a .o, it's too late.
Okay, that makes sense.
Okay, cool. All right. Other questions on logistics of PA5? We're still going to talk more about maxval and the knapsack problem, but as far as details about the programming assignment itself, what you're supposed to do, what your program should do, and so on. Questions about that? And I can show you some sample execution. So here I'm just running it on the sample source file, and you've got to specify capacity as well as the file name. So I'll put in a capacity of 20, and there's the inventory, and it tells me the highest possible value is 800, which I get from putting in 4 cell phones. So my phones weigh 5 pounds each, so 4 of those fills my bag. If I do 21, I get a different solution. I put in 3 phones and a pencil, and I get a slightly higher value. Sorry, 4 phones and a pencil. If I do slightly less, I won't be able to fit 4 phones, but I'll get 3 phones and 2 pens, and so on.
So the basic algorithm is it just divides it by the biggest value and then slowly goes down?
No, that would be the greedy algorithm, but that's not going to work for us. So we're going to have to use this maxval function that you get by finding the largest of these different possibilities. And so it's recursive, right? Maxval is going to have to call maxval typically a large number of times, and so we're going to have to add dynamic programming because all of those recursive calls are going to slow things down to the point where our program won't actually finish.
What do you mean by just dynamic programming?
Caching your results so that you don't have to always recall your recursive function. So pruning the recursion tree.
Oh, I see. Okay.
Okay. And so if we write a maxval function, for some capacity, we calculate the following possibilities. The value of item 0 plus the maxval of capacity minus the weight of item 0. The value of item 1 plus the maxval of our capacity minus the weight of item 1, and so on. The largest of these, that's the maximum value you can get from your original bag. And so this codes as just a for loop with a bunch of these calculations with a caveat. This is a possible value only if the weight of item I is less than or equal to the capacity of the bag. If your item weighs more than what the bag can hold, don't do this calculation, right? And it's not valid to just have maxval return 0 if it gets a negative number. This will give you an incorrect answer if you consider items that weigh more than what your bag can hold. So make sure when you're looping, you do that check.
So does that mean I can put it into a while loop? And if the capacity is greater, then I just go to another case where it is capacity is greater.
Yeah, so when you're calculating this and comparing it to your largest value so far, just throw that inside like an if statement or something. Make sure that your weight's less than or equal to the capacity. If it is, then you can do this calculation, compare the result to your best value so far, and if it's better, then save this as your best result so far. And then at the end of the loop, whatever you've saved as your best result, that's your final answer. All right, let me talk a little about PA4, and then we'll come back and we'll run through the maxval function in a specific case, and sort of I've got these worksheets I made up, and we'll track the inventory for each call to maxval and kind of see how we maintain that inventory to come up with an inventory for our original call. So we'll run through that in some gory amount of detail. But let's touch base on PA4 first. So PA4 is graded, and I posted comments for any deductions. And by and large, these looked good.
I used
So-
a couple flip days. How did people do on the delete function? It sounded like a lot of people weren't able to.
So a number of people nailed it. A number of people did not do it, which is fine. A number of people did it, but used a different algorithm. So it was kind of a mixed bag. So I'll talk about delete specifically in a couple of minutes. Makefile we talked about. Probably the biggest makefile issue that I'm seeing, and people got dinged on this for PA3, they got dinged on it again for PA4. If you have something like main GCC-O plate ... right? Or dependencies plate .o, etc., and then GCC-O plate ... When you say make tries to build the first target, right? It's trying to build something called main, and if you're building an executable called plate, right? When you say make again, it's going to say, oh, I haven't made main yet, right? And every time that you say make, it's going to redo this linking step. And that's obvious when you're testing your make file, because like I said, if you say make twice in a row and there's no errors in your source code, the second one should say everything's up to date. So if you say make twice in a row and it keeps executing this, go back into your make file and make sure that you're building the target that you're telling it you're building. So that's a make file thing, but like I say, a lot of people had issues with that, so I changed that to -5. Most people were able to read the database file, which is great. The file pointer business and all that stuff, people figured that out, so that's awesome. Not being able to look up license plates, so this is a problem because it makes a lot of the other testing difficult to do. You need to, if you're just using fgets and taking the string you get and passing that directly to your search function, you got to deal with a new line at the end. If you run it through scanf, you can use that to get rid of the new line, but it's cleanest just to do that business with string length -1, get rid of the new line like that. Fixed size arrays, I don't think I saw any of that. Delete command. All right, so I didn't intend you to try to find an algorithm that matched what I was describing, right? My intent was to give you the algorithm I wanted you to implement, and I did that several times, and the algorithm was exactly the following: replace the root with the largest node from the left subtree. That's the whole delete algorithm, except when there is no left subtree, and in that case, just move the root down to its right child. and some people tried to do that and got tangled up with trying to find the largest node, or having the left child or the largest be adopted and so on. That's fine. But about 15% of the class implemented a completely different algorithm. And it was actually this algorithm that about 15% of the class implemented for delete, which is, see if the root is null, which you don't have to do, and then do these recursive checks, and if you don't, see if the left is null, which was part of our algorithm, and then see if the right is null, which is not part of the algorithm, and then find the min thing and copy the value from the largest node to the root, which was not part of the algorithm, and then make another recursive call to delete, which was not part of the algorithm. This will work, but this is a very different algorithm. For one thing, this is copying the value from the node you want to delete into the root. And we don't want to do that. And if you did that without freeing the memory from the root node, reallocating memory for the plate first name and last name, your code will segfault. And so this is a much more complex approach to trying to delete a node, and it doesn't match what we're trying to do. And so I'm definitely not going to give you, when we're going through an assignment, all the code that you need to implement a function, but I will generally give you an algorithm and say, for example, start with the root, see if there's anything to the left. If there's not, just change this to be the root, free this from memory. If there is a node to the left, all of our work happens in this subtree. And there's two possibilities. If there's nothing to the right, then just change this to be the root, adopt this on the left, free this from memory. That was case 2. Case 3, in this subtree, if there is something to the right, walk down here, keep track of your current node and your previous node until you get to a point where there's nothing to the right. This is parent, this was largest of parent. And now have largest parent adopt parent's left on its right, and change your parent so the left child is here and the right child is here. Free the root, return the parent. So that was the delete algorithm that I was asking people to implement. And yeah, juggling the nodes is tricky, right? Temporary variables help, make this, root, make this, left tree root or something like that, and then move down and have, like a parent and the largest of the parent or something like that. And when you get to the point where, there's nothing to the right of your parent, then you can, left parent right equals parent left, and parent left equals root left, and so on and so forth. And so temporaries usually make these kinds of things easier. We may look at some tree balancing later on, and you'll see lots of temporaries being used to keep track of where you are in the tree. You don't need to do that. You can do, parent arrow, arrow right, arrow left kind of stuff. But this makes things a little bit easier.
I think my biggest issue with this is that it takes up a lot of time to try to make sure the code is working right, and I didn't have that lot of time, so.
Yeah, so this is one of these things where I think I said, 2 or 3 days on the delete function would be not unreasonable, and a lot of that is debugging. And this is a really good case where GDB helps a lot, right? If you're doing this and things are disappearing, you've got an algorithm written out, you go through GDB, you execute each statement, and you say, okay, so here I should be adopting the parent's left child on my right. Execute that statement, now check the parent's right child and see if it's adopted, this thing's left child. And if you step through, line by line, you should find a spot where you can see that, something that was supposed to happen didn't happen, or something happened that was different, or something happened only partially. but this is largely an opportunity in getting better with debugging. Surprising lack of comments in code, by the way, especially in the delete function. A lot of people had delete code that worked, used the wrong algorithm, no comments anywhere in sight, and it's a little hard to kind of go through what exactly the function's doing, especially if it's not working correctly, if there's not comments explaining the purpose of each statement or each section. Let's see, trying to get the largest left node's pointer go up to the recursive stack and having the parent of the largest left node have its pointer set to the largest node. Sort of unable to figure out. So a lot of that is handled by the recursion, right? We don't have to, once we adjust this root node, it'll pass back up to the parent. If we called delete recursively by saying something like, root left equals delete root left, or root right equals delete root right. Once we're in this subtree, right, starting with left tree root or something, there's no recursion involved in here. This is just a loop. It's pure iteration. And this is, marching down, arrow right, arrow right, arrow right, until you get to the end here. I'll show you some sample code in a bit where I did this without temporary variables. But it's marching down as far to the right as you can, but not too far, right? So that this is the last node. And as you do that, you just remember the node you were on before, so you got your parent. And if you've got something pointing to this, something pointing to that, then it's relatively few statements to do the final assignments that end up making this thing the root of the tree. Let's see why the car star plate is in the prototype and function call. The car star plate. So, for example, when you want to add something to a tree, right, we always have to pass in the root. That's the tree we're going to add to. These are strings, right? The way we declare a string is car star. We don't know how long these strings are, so we don't want to say car plate bracket, 800 or something like that. It's just a car star.
He's talking about the delete function.
Delete function? The plate is the thing that you're trying to delete, and that's a string, so it's a car star, right? But that tells you.
I don't understand what mechanism we're supposed to use to search for it. If we're supposed to, because you gave us stuff for finding the root.
Mm-hmm.
I don't.
So you string compare root to plate, right? String compare takes two strings, so root arrow plate is one string. Plate, the argument, if you called it plate, is the other string. Pass those to string compare. If string compare returns 0, then those strings are equal. If it returns something negative, then, if I compare plate to root arrow plate, if string compare comes back negative, it means plate comes before the root, and so I want to delete from the left subtree. Otherwise, I want to delete from the right.
I just feel like that there would be an edge case where you would only go down one right tree, you would only go down a tree that's to the right of the furthest left, almost furthest left node.
Mm-hmm.
But then there would be a branch off along that.
Mm-hmm.
To the,
Right. I think you're thinking about the part that's going to be done by the recursion, and if we don't keep thinking about that, then it feels like sometimes we need to do something special at the root, right? We need to see if our thing is bigger than the root, is it equal to this maybe, and if it is, do something special there, right? We really don't have to do that. If we believe the delete function will delete this plate from this tree, and return the new root, right? Then if we know our plate sits to the right, all we have to do is call delete with this as the root. And have faith that, you know, something will happen in that call to delete, probably some more recursion, maybe not, that will remove the plate from this tree and return the root of it. And if we say root right equals delete root right comma plate, that will make this point to that modified tree. And so even if what we're deleting is, say, this thing immediately to the right, that will still work. What will happen, though, is when we call delete on this tree, the first time we go through the delete code, it'll say, hey, I'm deleting the root. It'll replace this with whatever the largest value in this thing's left subtree is. And when we get back from delete, we'll get a pointer to that node, because that's the new root, and delete always returns the root. And so our original call delete will say our original root on the right should point to that new node, which was the largest node from the left. And it kind of magically works, but, you know, not totally magic, because we're writing the code, we're telling it to work, and so it's doing what we tell it.
I think about like recursion as like you're recalling the same function and forgetting about the previous values.
Mm-hmm.
And that's kind of the tree works, right? Like,
Yeah.
you don't need to, like, if you're doing a constant comparison, forgetting about the last node because it doesn't really matter anymore, and just go down to the largest node that way. That's
Yeah.
the type of idea.
Yeah, exactly. So I was going through this weekend looking for some ideas on how to explain this recursion better, and one example I saw was writing a set of delete functions, a delete function for this level, a delete 1 for 1 level down, a delete 2 for 2 levels down, and then thinking about, you know, when I'm doing delete 1, I call delete 2 to delete from these subtrees. And that might be a helpful way to explain this. I'm not sure. I'm kind of, every time I teach this, I'm rethinking different ways to approach this. It's fundamentally a concept that needs to get wired in our brains, and all I can do is kind of, you know, try to present the things that will help your brain do that rewiring. But it is a confusing concept, and it's counterintuitive in a lot of ways, and so I'm still trying to figure it out. But the way you just described it is correct, and that kind of goes along with the idea of maybe thinking that here we're just calling another delete function, right? Let's see. You said earlier that in delete you don't need to check if root equals null, but if you omit that, would you potentially get a seg fault when checking or navigating root right? So if you call search before you ever call delete, right, and you specify that delete only works if the thing you're trying to delete is actually in the tree, so make sure you call search, then you should never get to a case where delete is called with a null root, right? Because that would imply that the thing you're trying to delete isn't part of the tree. And so, you know, I told you I wasn't going to try calling delete on something that didn't exist. And in your main program, call search first. And you're guaranteed you're going to find your plate before you run out of root nodes to look for. And, you know, if there's nothing to the right, we don't have any special case to deal with. We take the largest thing from the left subtree and we change that to be the root. And the right will be the root's original right, which is null. That's not a special case. And you know, most of these special cases aren't actually special cases. It's really just those three situations. So recursion is used to crawl to the desired node to delete, and looping is done to handle a large left node and its parent business. Exactly. Yep, that's correct. It's a good way to put it. Recursion is like subtracting, no one gets paid. Yeah, actually the person who gets paid is the one who says, you know, when you're searching for something, if the tree is null, return 0. When you're calculating the height, if the tree is null, return -1. When you're calculating balance, if the tree is null, return 1. Right? That's the only one who's actually doing any work. everyone else is just sort of like, hey, answer this question for me, right? So it is like subcontracting, also in the sense that, you know, the people doing most of the work are the ones that don't get noticed sometimes. Let's see, how are we supposed to do recursion in the add function? So add is similar to delete, but it's a little easier to think about than the delete. So node add. So the base case is where there's nothing in the tree, in which case we have to create a new node with the plate and the first and the last name in it and the children pointing to null and so on, and we just return that new node. We go from an empty tree with nothing in it to a tree containing one node, right? So that's the base case. Otherwise, if plate is less than root plate, so do a string compare, right? If string compare plate and root plate is less than 0, then we want to insert to the left subtree. So call our add function on root left, pass it the plate and the first name and the last name, and when we come back from this add function, the return value of this will be the root of the left subtree after this plate has been added to it. And so let's set root left equal to what add returns. Otherwise, add it to the right. So again, the only real work is happening in the base case. That's where you actually create a node and you copy in the plate. You malloc space for the plate first and last name. You string copy those in. You set the left and right children to null and you return that. That's the only time anything's actually really done. Everything else is just making calls to yourself. But if we believe that this will add the plate to the left subtree, then this is the right thing to do. Add the plate to the left subtree and change my root to point to that new tree on the left. Or add to the right subtree and change my root to point to the new tree on the right. And, yeah, let's see. Yeah, once you get recursion and it really makes sense, right? Then it looks very straightforward, right? But the whole point of, in some sense, 222 and CSE215 is getting to that point where we can look at this and it actually starts to make sense. So not doing this is not, you know, it's not a silly mistake or anything like that. It's kind of, you know, the essential part of the learning process. Let's see. Yeah, so I don't know if this is related to the question in chat, but you know, if you have a pointer, you can do star pointer to dereference the pointer. That's, for example, a struct node, and then you can say plate, right? Don't do that though, right? A few people are still doing this. Stop. Don't do this anymore. I'm not taking off points for it. You may get a 0 at a university if you have something like this in your code. I can't guarantee what the teacher will do. The way to do this is to put the name of the pointer and then an arrow and then the field you want to dereference. And I'm pretty sure. Yeah, go ahead.
I just think that looks nicer. Well, not the one that university disagrees, but the one that agrees.
Yeah, this one?
Yeah, I like that one better.
It looks nicer and it works nicer when you're iterating and so on and so forth. And people who are doing this, I don't know if they're just being contrarian or if they don't understand that you can do this also. And I'm okay with being a rebel. Just be sure that when you're in other people's courses, right, don't do something like this, because at the very least you'll raise eyebrows and probably lose points. But I know some teachers who might just like give you a 0 on the assignment, just because people are that way sometimes. Algorithm wise, I tried. Go ahead.
I'm sorry about that, but basically, my original question was like, I've seen when people would kind of access data in a struct, they don't use pointers, but they use like the name of the struct, and then they put like dot the name of the variable in that struct.
Mm-hmm.
And it's wondering like if there's a benefit of using pointers versus just straight up accessing it without a pointer.
So the main difference is that when we've got structures like linked lists or trees, something like this, if we had a struct node, if we tried to say something like this, that's not going to compile, right? This is an infinitely self-referential descending hole of pain, basically, because we're saying, okay, what does a node contain? Well, it contains a field called left, which is a node. Well, what's a node? Well, it's a thing containing a field called left, which is a node. And the poor compiler, if it tried to actually implement this, it would be, sort of an infinitely long structure, because this node actually contains a copy of itself. And we can't do that with most programming languages. Right? We can't actually have a node that contains a node inside it. If you remember 215, this is like a self-consuming set. It leads to like universe-ending paradoxes. So if we make this a pointer to a node, no problem. What's a pointer? It's 8 bytes. Okay, well I can set that up and the compiler can go on about its business. And so that's one reason why we use pointers. Another reason is that we want to pass things to functions. We want to return things from functions. We want to store, things in arrays and so on and so forth. Pointers are basically 8-byte integers, whereas, a actual node might be a field containing, 100 different things to it and so on and so forth. And so that's the other reason we use pointers. But there's cases where, you could declare your root to be a struct node, and then every time that you pass it to a function, you could pass ampersand root to pass its address. And that works fine, but it doesn't look as clean as just passing root. And when we get to Java in 223, all of that goes away because we don't deal with pointers. And the quirks of C will be more obvious then that, oh, this was just a quirk of C, as opposed to, there's some reason why we wanted pointers. So, quick comment on algorithms, right? So I'll give you an algorithm for the maxval function for PA5. I won't give you, all the code for it. I'll usually spec out some sort of pseudocode, but that will tend to go away in university classes also, right? You may be told, okay, you're going to use the such and such algorithm. Go look that up, right? And you'll be expected to figure out on your own, what the algorithm is for doing something, and then write code for it. And so going from a description of an algorithm, the steps to do some process, to code will be a challenge. And then at some point you may not be given something for which there's an existing algorithm. You may be told, figure out an algorithm to do such and such. And that's sort of the most challenging. Yeah, go ahead.
I think there is a class at W2 that explains about making algorithms.
Mm-hmm.
So basically, just instead of having to think, like, of course you still have to think about it, but there's classes that provide strategies or recursive series that have some sort of pattern, and then create an algorithm from that.
Mm-hmm.
Basically, you're making your own math equation that satisfies the situation.
Mm-hmm. Yeah, so you'll take an algorithms class at a university, which will cover, you know, a lot of different algorithms, different classes of algorithms, look at complexity of algorithms, look at proving algorithms, and all this kind of stuff. And that exposure will help if you know, come to a situation where I need a way to, you know, do such and such to this data while maintaining this and also satisfy this requirement on efficiency, right? And you'll be able to take, you know, your understanding of different algorithms and your higher level understanding of algorithms abstractly and put those together to come up with, you know, something new. And that's part of you know, what you come out with a bachelor's in computer science with is those kinds of abilities. So there's lots of good stuff down the road related to algorithms, and so mostly we're focusing in this year on, you know, implementing algorithms and understanding how they work and being able to write the code and debug the code and test the code and so on and so forth. And so this is all good practice. 15 people in the class. That's fantastic. Thank you. Good to have people here. All right. Let me do a quick run through on some sample code from PA4. This does not match the assignment. This is code I wrote a few years ago when I was thinking about doing a tree balancing assignment. But just some sample tree functions. So, oh yeah, I didn't finish going through the assignment. So other issues, balance functions. So balancing a tree, telling if a tree is balanced, you need three things to be true. Left tree is balanced, right tree is balanced, and the height of the left and right trees are within 1 of each other. And some people only used some of those conditions. Some people checked to see if left and right were balanced and called it good. Some people only checked to see if the heights were close and called it good. A number of people did height of the left minus height of the right and checked to see if that was less than or equal to 1. And being less than or equal to 1 does not mean the absolute value is less than or equal to 1, because negative 10 is less than or equal to 1. But if the height of the left and right subtrees differ by 10, your tree is definitely not balanced. So that's an issue that some people ran into. Inserting into a tree, if the root's null, return a new node. So I made a new node function. You don't need that, but new node just creates a new node. Otherwise, if the plate sits to the left, insert to the left and return that. You know, store that on the left of the root. Otherwise, we're going to insert to the right, so insert to the right, and set root right equal to that, and then return the root. This was stuff for balancing the tree, which we're going to talk about later, but you didn't have to do in here. New node, this looks a lot like PA3, right? So to create a new node, malloc space for a struct node. A few people did a struct node star. That's not enough space. A few people did size of temp. That's not enough space, right? You need enough space to store a node that's the size of struct node. And then figure out how many bytes you need for the first, last name, and plate. Malloc one more than those and do a string copy. Set the children to be null and return that. Traverse, I just did one traverse function that basically prints the data in the right spot in between traversing the left and the right. That's just, you know, a shortcut. Search, so for searching in a tree, right, make sure that you compare the plate to the root to decide which side to search on. So certainly if the root's equal to the plate, you're done, you found it. copy the data from the node into your arguments first and last. But some people just called search on the left and search on the right. Don't do that. That's a exponentially larger amount of work, right? Compare your root to the plate you're looking for. If the plate sits to the left, just search the left and return that value. Otherwise, search the right and return that value. And search, remember, is going to copy the first and last name into these arguments. So when I return, these arguments will be populated with the first and last name. And then freeing the tree frees the left and right subtrees recursively if there's anything there, and then it frees the root node, and freeing the root node is freeing the malloc strings and then the root itself. Height, if the root's null, return -1, otherwise find the left and right height and return the largest of those +1. Balance, if the root's null, return 1, it's balanced, otherwise find the height. Find the absolute value of the difference. If the difference in height's too big, return 0, it's not balanced. If the left is not balanced, it's not balanced. If the right is not balanced, it's not balanced, otherwise it's balanced. And then delete, if the root's null, return null. No deletion necessary. You don't have to do that if you know that the node's guaranteed to be in the tree. Compare the thing you're deleting to the root. And if it's not equal, we're going to do a recursive case. So if the string compares negative, delete from the left. Otherwise, delete from the right. So all of this business here is where we're going to delete from the root, right? And so check the left subtree. If the left subtree is null, there's nothing on the left. Save the root's right child to be our new root, free the root, and then return the new root. So that's this business of deleting the root of this tree. There's nothing on the left. Just make this thing the new root. And then free that from memory, return the new root. Otherwise, let's go into the left subtree. So I set temp equal to root arrow left. So here's temp. And we want to find the largest node in this thing's tree, which means start from the root temp and go as far to the right as possible. So, so we know temp exists. If temp right is null, there's nothing to the right. Temp is the largest node. And so temp left will stay exactly where it is. It'll just continue to pick up this stuff. Temp right, which is null right now, should pick up root right. So we do that right here. We get rid of the root. We return temp. That's case 2. Otherwise, we've got our most general case, which is this loop right here. And so we have some stuff here. And so I decided to use look ahead in this. Well, temp right is not null. So temp exists and temp right exists. And so temp right is not going to segfault. I only know that because I checked up here to make sure temp right is not null. So I'm just using one variable temp. And if temp right is null, then I'm going to exit out of my loop. Otherwise, I'm just going to sit here and move to the right. So when I'm done with this loop, temp is actually the parent of the largest node because temp right is null. So temp right is the rightmost child. That's the largest one. So I save that in a local variable. I call this return. That's the value I'm going to return. And then temp right picks up temp right's left child. So if this had stuff on the side, I pick that up so it's not orphaned. And then the return node, which is this one, I set its right child to root right, set its left child to root left, I free the root, and then I return this node as the new root. So that's the unnecessary case where the tree is empty. This is the check to see if you're deleting the root. This is case 1 where there's nothing to the left of the root. This is case 2 where there is something to the left of the root, but that something has nothing to the right. And this is case 3 where there is something to the right of the left subtree's root, and so you move down until you get to the largest node in the parent, and you make those adjustments. And then these are the recursive cases where you traverse into the tree, and whatever you get from deleting in a subtree, you use that to replace the left or right child of the root.
Wait, did you show us what will happen to this nothing on the left?
Yeah.
There's only nodes and right?
Yeah, so if root left is null, then we're going to basically return root right as the new root. So save that in the temporary, free the root, and then return the new node. So that's this case. There's nothing on the left. This is going to be the new root of the tree. And that was special case 1 for deleting. Nothing on the left, so we can't find the largest on the left. But since we're deleting the root, just make the right child the new root. Free that from memory, and you're done.
And do you typically do this in order from like top to bottom when it comes to like case numbers? Like case 1 would be the first thing to check, and then it kind of goes down the function list from top to bottom.
Yeah, because if root left is null, and I set temp equal to root left, this is going to segfault. Right, because temp left is, if root left is null, then null arrow right, that'll segfault when I try to dereference null. So I do this case first because this is assuming I've got at least one node on the left. So that has to come first, and then once I know I have something on the left, I have to take care of the case where I have something on the left but nothing to the right of that. Because my third case is checking to see what this node is equal to, or what this thing's right child is equal to, and if this is null, I can't access its right child. So yeah, the order definitely matters. And usually when you're trying to put together an algorithm, right, you want to think about doing things in a certain order, largely because you're building up complexity, right? Just like when we test something like balance, for example, right? First thing you want to do is check to see if the tree is null, right? Because if I don't do that check first, this is going to segfault if root is null. So I kind of have no choice but to take care of that case first.
So is the kind of the pattern here is that you always check if the node you're trying to access is null before you start manipulating it.
Yeah, if there's a possibility of something being null, you want to figure that possibility out and take care of it before you try to do something where a null node would be a bad thing. It's the same thing as when you're parsing command line arguments, right?
Can you go back to that?
Don't try to scan argv bracket 5 unless you check argc first and make sure this thing has a fifth element, right? Otherwise you risk a segfault. Go back to this.
Yeah. What's that? Oh, so. Okay, thank you. Yeah, I just wanted to look at that balance.
Okay. This is just an absolute value function. You can do an if statement.
Yeah.
Yeah, if h1 is bigger than h2, d equals h1, else d equals h2.
Nope. Nuh-uh.
There's also a there's an abs function in standard lib that takes an integer, returns an integer, so that works. All right, let's do a break. Let's come back at 11:15, and we will go through maxval in more detail. All right, we're back. Let's see. All right, let's go through the maxval behavior. And I'm going to use this this sample inventory that we started with last time. So we're working with an example where we had like item 1, which had a weight and a value. So item 1 had a weight of 2 and a value of 1. Item 2 has a weight of 3 and a value of 9. Item 3 has a weight of 4 and a value of 13. So we'll keep this inventory file handy, and you know, when you open the flat file and you read it in, you save that into an array. And you're definitely going to be better off if you make some structures for PA5. So have, you know, a structure for an item that contains a name and a weight and a value, for example, and then, you know, to read in the flat file and save the list of items, it's just an array of whatever that structure is. And item n is just array bracket n, and item n's weight is array bracket n dot weight, and so on. And so there's an example someone asked earlier where you would probably use a dot instead of an arrow, because an array of struct items, right, each element is actually a struct item, not a pointer to a struct item. And so we dereference with a period there. All right, so say again.
I'm actually kind of excited for this new kind of struct, because we haven't covered like acting struct just without pointers.
Yeah, it's a nice change. All right, so let's look at the maxval function, right? And let's go for broke here and do a bag with a capacity of 10. That was our example. And with a capacity of 10, the greedy solution would be put in 2 of item 3 for 26 and 1 of item 2 for 1 is 27. That's not your optimal solution. You get a better solution by doing 1 item 3 and 2 item 2s, which gives you 9 plus 18 is 31. So 10 is an interesting example where the optimal solution is not the greedy one. We'll calculate 6 along the way, and that's another solution where the greedy approach doesn't work the best. All right, so our main loop, remember, is something like the following. So here's maxval. So best equals 0 for I equals 1 to whatever the number of items is. If the weight of item I is less than your capacity, let me call it at least cap, is less than your capacity, possible equals the value of item I plus whatever you can get out of a capacity that's been diminished by the weight of item I. If possible is better than best, then set best equal to possible. And do all of this in a for loop and then return best. So that's basically PA5, right? One for loop with an if statement in the middle. there's a few details to do. So I'm just going to do a running maximum, right? Because I don't have a function that I can pass an arbitrary number of arguments to. So it's like a running sum. Initialize my best value I've seen so far to 0. And then for each of my items, if that item fits in the bag, take the value of that item. Imagine a bag that already has something with that weight in, and see how much you can get out of a bag like that. With that capacity, add that to the value of the item. That's what we can get if we put this item in our bag. If that's better than the best solution we found, let's remember it. And then at the end, we're going to return best. All right. And so, lots of details to add to this. One of them is dynamic programming, right? Save your answer at the end. Check for a saved answer in the beginning. We'll do that on paper. Another detail is tracking the inventory. We're going to do that on paper. But this is the basic gist of finding the maximum value. So what I want to do is go through some of the recursion and get an idea what actually happens each time we make this call. What do we pass to maxval? What do we get back? All right. So let's start off. We've made a call to maxval of 10. And we want to get back a maximum value and an inventory of items. All right. So what does our maxval function do? Well, it does 3 calculations. It calculates these 3 values, and it tries to find the largest of them. So the first thing it's going to do is take the value of item 1, right? And item 1 is worth 1. And it's going to add the maximum value we can get from the bag after we've put item 1 in. Now our bag holds 10 pounds. Item 1 weighs 2 pounds. So it's going to take 1 plus maxval of 8. That's going to be the possible value we get for item 1. I'll peek ahead before I do the recursion, but you know, the actual code would recurse right here. But I'll go ahead and fill this in first, and then we'll do the recursion. So item 2 will be worth $9. Since it weighs 3, we'll have to find maxval of 7, add the result of that to the 9. Yeah, I can post these worksheets. Never had anyone ask for that, but that's a great idea, actually. I'll go ahead and post these on Canvas. And then item 3 has a value of 13, but it weighs 4. Our original bag held 10, so we're only going to have a maxval of 6 at that point. All right, we're going to find the 3 values of these. Whichever one is largest, that's going to be maxval 10. And the inventory of items that gave us the corresponding maxval, that's going to give us our final inventory. All right. Do you want the blank worksheets or the worksheets that we're filling out? I was thinking you meant the blank ones. All right. So let's calculate maxval of 8. All right. So this is a recursive call. Inside our loop, we're going to say, let's calculate maxval of this. That's going to be maxval of 8. So we're going to make a call. All right, what does a recursive call look like? We forget about all of this, and we simply make a request to say, hey, find me maxval for a bag with capacity 8. Yeah, I can do both. All right, how do we do maxval 8? We're completely forgetting about our original call to maxval. Now all we're seeing our entire universe as, hey, I'm a CPU. Someone just called this function with an argument of 8. I'm going to find the answer, right? Doesn't care about maxval 10 or anything like that. So how do we find maxval 8? Well, we're going to go through this loop, and we're going to do the following calculations. If I put in item 1, that's worth 1. The item 1 weighs 2. Our original capacity was 8. That leaves us with 6 pounds of capacity. So we're going to calculate maxval 6. Item 2 is worth 9, diminishes the capacity by 3, so we'll need maxval 5. And item 3 is worth 13, diminishes the capacity by 4, so we need maxval of 4. All right, well, as soon as we go the first time through our loop, we're going to say, hey, I need to call maxval of 6, another call. So this gets saved on the stack, which is this little pile I have on the side of my desk, and we make a new function call. and we say, hey, let's figure out what max val of 6 is. And, you know, there's my stack over there. So that's sitting there in memory, and I'll come back to it when I return from my call to max val 6. I'll figure out what max val of 6 is, and then I'll go on to max val 5. So let's just keep recursing here. So capacity of 6, what's the max val? Well, got to do 3 calculations. Value of 1 plus max val 4, value of 9 plus max val 3, value of 13 plus max val 2. Is everybody clear where these are coming from? Right, if I put in item 3, it's worth 13, it weighs 4 pounds, my bag holds 6, so the remaining space in the bag is only 2 pounds. So whatever the most value is I can get from a 2-pound capacity bag, if I add that to 13, that's the most I can get if I start with item 3.
Looks like you're using some kind of recursion, right?
Oh, yeah.
You're calling the same function over and over again?
Yep. Yeah, so we're 3 levels down, right? I called max val 8, which required calling max val 6, which is what we're doing right now, but this is going to require us to calculate max val of 4. We're going to make another recursive call. There's a base case here. Yeah, go ahead.
How would you store these numbers? How would you kind of store these numbers? Just so you know what I mean, right? Like,
These numbers?
Yeah.
Make an array.
Well, I think how much those is the capacity, so that way, you know, to prevent what do we call it? To prevent like slowing down. I don't know what to call it.
Oh, you mean
the same value, so it doesn't like we call it.
so the dynamic programming piece.
Well, yeah.
Yeah. So I'll have an array of you know, I'll have an array of saved values, and in the beginning, right, I'll look at my capacity and see if I've got a value saved in my array. If I do, I'll just return it. Otherwise, at the end, I'll do something like save bracket capacity equals best. I'll save it in this array before I return. And the next time I come in, when I check save capacity, if I've already calculated this, I'll see my value in there. And so I'll return from there. But our cache is going to have not just the maximum value, but also an inventory, and we may as well put in a flag to say if something's been saved or not. And so that'll be a structure you'll want to define and make into an array. And it'll probably be an array of 1025 because our highest capacity is 1024. There's a base case in here also that I've skipped. If the capacity is 0, we'll just return 0. We don't really need that as a base case because if the capacity is 0, none of these if conditions are going to be true. We're not going to do any of these recursive calls or any of these calculations, and when we're done, we'll have done nothing in this for loop, which means best will still be 0 and we'll return 0. But logically, it's nice to, you know, illustrate our base case right in the beginning there, which is if the bag can't hold anything, then we have no value that we can extract from putting things in that bag. So we'll use that to kick out of our recursive pieces of paper here. But let's get down to the base case. So max val of 4, we can have 1 plus max val of 2, we can have 9 plus max val of 1, or we can have 13 plus max val of 0. Alright, we got another recursive call to make, so this goes on to the stack, and now we have to calculate, we need more memory, we have to calculate max val of 2, and so this is what we're calling right now, max val of 2. And max val of 2, well, when we go through our for loop, we'll find 3 situations. The first situation is if we put in item 1, it has a value of 1, it weighs 2 pounds. Since our original capacity was 2, once we put in item 1, there's no space left. So we have no space left, so we need max val of 0. Item 2, which weighs 3 pounds, can't fit in here. And so we're not going to do a calculation for item 2. And item 3, which weighs 4 pounds, definitely won't fit in here. no calculation for item 3. So now we need to make a recursive call to maxval of 0. And when we call maxval of 0, it's going to return a 0. So that call will return very quickly without doing any other recursion and tell us we've got a 0. Okay, that's our first return in all of this. We've gone, 4 or 5 levels down the recursion stack, and we've just gotten our first return. So we know maxval of 0 is 0. And the inventory for a maxval of 0 is 0 of each item. Alright, so let's talk about the inventory. The inventory is the count of how many of each item I use in order to get this maxval. In my calculation, in my loop for determining maxval of some capacity, right, this first solution is saying, suppose I start by putting 1 of item 1 into my bag. Alright, my maxval of 0 comes from this inventory. This entire solution comes from finding the solution for a maxval of 0 and then adding 1 more of item 1. So here's the only work you do on the inventory. You bump up this count from a 0 to a 1. That's where the whole inventory tracking comes. It's one increment. In this case, I start with item 1, so whatever solution I get for maxval 0, I'm going to add 1 more of item 1. I have no calculations for item 2, no calculations for item 3. My maxval here is 1 plus 0 is 1. That's my best solution. So now I've got the solution to my call to maxval 2. The maximum value is 1, that comes from right here, and the inventory is 1, 0, 0. Which is, 1 of item 1, which weighs 2 pounds and has a value of 1. So that's a pretty obvious solution, but that's how the code figures it out. Alright, we're ready to return from a recursive call. Over here we made a recursive call to maxval 2. That call is now returning, and it's telling us 2 things. It's telling us the maximum value is 1, and the inventory that gets us that is 1, 0, 0. Alright, again, this solution says take the solution for maxval 2 and let's add 1 more of item 1. So we're going to bump up the count of item 1 to a 2. And now we're ready for another recursive call. Let's calculate maxval of 1. Well, with a capacity of 1, we go through and we say, well, item 1 weighs 2 pounds, that's not going to fit. Item 2 won't fit. Item 3 won't fit. Nothing's going to fit into our bag. The maxval is 0. The inventory is 0. We don't record that as a base case, right? We might have an item that only weighs 1 pound. But this loop, right, if our capacity is 1 and every item weighs more than 1, none of these statements are going to execute. There's no recursive calls. Best never changes, and when we're done, best is just 0. So we've got our solution for maxval 1. The value is 0. The inventory is 0. So we come back here, and now we know that that maxval of 1 is equal to 0, and the inventory is 0. And so trying to solve maxval 4, we start with item 2. We got a possible value of 9, and the inventory that gets us there is the inventory for maxval 1. But we bump up item 2. So we change this from a 0 to a 1. This should still be making sense, right? If we start with item 2, that has a value of 9. It has a weight of 3, so it's going to take 3 of those pounds, and there's nothing left we can put in that last pound. And the item count that gets us that 9 is, none of item 0, 1 of item 1, none of item 1, 1 of item 2, none of item 3. Alright, and then our last call, maxval of 0 is equal to 0 with no inventory. So if we start with item 3, our best value is 13 plus 0 is 13, and the inventory that gets us this is the inventory for maxval 0, but we bump up the count of item 3. Maxval of 2 was 1. And so 1 plus 1 is 2. Alright, so we have finished this for loop in computing maxval 4. And what do we know now? We know that, our absolute best maximum value for a capacity of 4 is either 2, 9, or 13. Which one's largest? 13. So the max val here is 13, and the inventory that gets us 13 is 0, 0, 1. Well, we're finally done with the call to max val 4, so we can return that 13. Max val of 4 is 13, and the inventory that gets us that is 0, 0, 1. Alright, so our first case in trying to find max val 6, 1 plus max val of 4. Max val 4 is 13, this is 14, and the inventory will be the inventory from max val 4, but we bump up the count of item 1, so this changes from a 0 to a 1. And now we have an actual solution, right? We're saying we can get 14 out of a bag that holds 6 by putting in 1 of item 1, that's this thing right here, and 1 of item 3. So that's our 6 pounds, and 1 plus 13 is 14. Alright, we need to find max val of 3. Another recursive call. So if we have a capacity of 3, what's max val of 3? Value of item 1 plus max val of 1, value of item 2 plus max val of 0, and item 3 does not fit. What is max val of 1? Well, go back to your cache that you're building. That's my stack of papers, and hey, I already calculated max val of 1. I don't have to do all that stuff. I can just say, hey, max val of 1 is 0, and the inventory is 0, 0, 0. So now we're starting to speed up, because we don't have to keep doing this recursion, right? We can just read our values off our sheets of paper. 1 plus 0 is 1, and the inventory that gets us this 1 will be the inventory for max val of 1 with item 1 bumped up by 1. Max val of 0 is a base case, that's 0 with no items. 9 plus 0 is 9, and the inventory that gets us that 9 is the inventory for max val of 0 with item 2 bumped up by 1. Which one is largest? Looks like this second case is the largest, so we're going to return a max val of 9, and the inventory that gets us that will be 0, 1, 0. Well, we've done max val of 3 now. So now we can come back through our recursive call. We've calculated max val of 3. What did we find? Max val of 3 was equal to 9, and the inventory was 0, 1, 0. That's the inventory that gets us 9. 9 plus 9 will be 18. And we get this 18 by taking the inventory for max val of 3 plus bumping up the count of item 2 by 1. So this goes to a 2. All that this is saying is that, hey, if you put in 2 of item 3, you can get $18 out, right, from a bag that holds 6. That's what this solution is storing. Let's do this last one. 13 plus max val 2. Well, guess what? Yeah, go ahead.
Question is that when we're comparing inventories of first, second, and third values, are we just comparing like the values of them?
Just the max val.
Yeah, just comparing the max value, and then trying to create some kind of condition of which one's the largest, and then return that for the next recursive function.
Yep, exactly. And the inventories kind of come along for the ride. They don't really participate in finding the max val or choosing which case to use. So max val 2, we'll go through our cache and see, hey, we already calculated max val 2. We know max val of 2 is equal to 1, and we know the inventory for that 1 is the following. And so we can get, 13 plus max val of 2, 1. We can get a total of 14. And we get that by taking the inventory for max val 2 and bumping up the count of item 3. So now we're ready to answer the question, what's max val of 6? we'll find the largest of these three numbers. Looks like it's this case right here. So max val is equal to 18, and the inventory is 0, 2, 0. And so now we're ready to come back to our recursive call here where we tried to find max val of 8. Well, our first recursive call was 1 plus max val 6. Max val of 6 is 18, and the inventory for that is 0, 2, 0. 1 plus 18 gives us 19, and the inventory for that will be 1 of item 1, 2 of item 2, 0 of item 3. All right. I'm going to call it good there unless people want to keep going, but basically, right, we would do the same thing to find max val of 5, which we haven't calculated yet. Well, let's do one more. Let's do max val of 5. We got space left on the stack. Let's calculate max val of 5. And I think we've got enough cached values to get an answer for that. So max val 5, 1 plus max val 3, 9 plus max val 2, or 13 plus max val 1. All right, max val 3 is equal to 9. We've calculated that, and the inventory is 0, 1, 0. So 1 plus 9 is 10, and we'll bump up the count of item 1. All right, max val of 2, we've calculated the max val of 2 is 1, and the inventory is 1, 0, 0. 9 plus 1 is 10, and we bump up the count of item 2. Max val of 1, I happen to remember, is 0 with no inventory, so 13 plus max val 1 will be 13, and we'll bump up the count of item 3. So which one of these is largest? Looks like this one right here. So max val 5 will be 13, and the inventory will be 0, 0, 1. So now we can come back here. We were trying to find 9 plus max val of 5. Max val 5 is 13, and the inventory is 0, 0, 1. 9 plus 13 is 22, and we bump up the count of item 2, so it looks like this. One more calculation, max val of 4. So max val of 4 is 13. And the inventory for that is 0, 0, 1. And so 13 plus 13 is 26, and we're going to bump up the count of item 3, so this will be a 2. So what's the largest of these? Looks like 26, this solution right here, with an inventory of 0, 0, 2. So we found max val 8. Max val of 8 is 26 with an inventory of 0, 0, 2. And 26 plus 1 is 27. So going through this can feel pointless. It can certainly feel monotonous and like we're just doing the same thing over and over and over again. But anytime you want to write a program, anytime you want to understand an algorithm and code it into, C or Java or something else, the first challenge is understanding the algorithm completely. Being absolutely 100% clear, what do I want my program to do step by step? What are the steps of the algorithm that I want it to execute? And going through something like this will help you understand that, right? You can see pretty clearly now that, when I find max val 6, I'm not going to do all that work I did before. I'm just going to say, hey, I already calculated that. The max val of 6 is 18, the inventory is this. And that tells me, hey, I need to have this information and this information stored somewhere so that if I go in with a 6, I can retrieve that and this. And very clearly, once I do this and I say this max val of 6 is 18 and this is the inventory, I'm going to do that value 18 plus that is 31, and since this is item 3, I'm going to bump up this count. And your goal is writing code to do what we're doing here on paper. Yeah, go ahead.
So are we storing inventory as a struct or inventory as a variables? Because it seems like every single time we call max value, we have to store the inventory value somewhere. Is it stored in? I'm assuming it's stored as a struct, right?
Yeah. So as we're going through the for loop and checking these cases, when we find a value that's bigger than the previous one, we need to remember that. That's what I'm calling best in here, right? And we also need to remember this particular set of values for how many of each item we get. So this can be an array of integers at this point, right? It can be an array called inventory. It's an array of 128 integers, and initialize it to zeros, right? But we need to get that value back from maxval. And so one approach would be to have maxval be a function that instead of returning an integer, returns something like an answer. And have answer be a struct that contains, integer value and integer item count, bracket 128. And now I can take the value that comes back from maxval, and that's a structure. And if I say, answer dot value, that gives me my 18. And if I say answer dot item count, it gives me this array. And if I answer dot item count bracket 2, it would give me the count of item 2, and so on. And so think about the steps you're doing on paper. Think about the type of information you need to keep track of, the type of things you need to do with that information, and play around with different structures, and see what's going to work best for your algorithm. And the general consensus among a lot of people seems to be that data structures is one of the most important aspects of programming. I claim there's 3 important aspects of programming. Data structures is one of them. The ability to look at a problem and decide, how am I going to organize the information, right? What kind of data structure am I going to use? Sure, do I want a linked list, a tree, a stack, or whatever? But even at a more fundamental level, right, what kind of information gets associated with what? What sort of access do I want to that? Do I want this to be an array or a linked list or something else, right? So deciding on the data structures usually happens pretty early in the process of writing a program. The algorithm comes first, but in the process of turning the algorithm into code, you need to think about, okay, how am I going to store this information? What kind of things am I going to use? That's the process of developing the data structures for a program. And the ability to do that is definitely one of the major keys to being a very successful programmer, in my opinion at least, and other people's opinions. The other things I claim are essential to being a successful programmer: ability to debug and the ability to do rapid prototyping, to write a function, build a test bed for it, and start exercising it. And get something quick and dirty up, and then start expanding on that. So the whole modularization thing. So those are the three goals that I have for people. All right. So we could do maxval 7, and we'd end up doing maxval of 5, 4, and 3, which we would still need to do maxval 5, and I'm out of stack space. But you get the idea, hopefully, right? And then when we do this, we'll figure out, what's the best value we get here, and it's going to turn out to be this one, 0, 2, 1. And so for a capacity of 10, we could do either 2 of these and 1 of those, or we could do 1 of these and 2 of those. I think they'll both come out to 31. Your maxval solution is not always unique, right? As long as it's a solution that gets you the best value, but there might be multiple ways to get that value out of your bag, and that's okay. And if you get a good solution and it doesn't match what the sample code does you, but it's the same maxval, and your solution adds up to that maxval, that's totally okay, right? You don't have to always get the exact same solution. For example, if both of these items weighed 2 pounds and they had the same value, you could use either one, right? And you get an equally good solution. So there's possible multiple solutions. All right, the other thing that should be clear here is that we are repeatedly calculating the same maxvals. Maxval 6, maxval 6, right? Gets calculated multiple times. Maxval of 2, maxval of 2, right? On the other hand, maxval of 9 never gets calculated. So we don't necessarily calculate every possible function value. Some values we will calculate a few times. Some values we'll calculate a lot. And that's where the whole dynamic programming, the storing of those values in arrays, will potentially save us a lot of time. All right, so questions on this? I'll go ahead and scan these and toss them in a PDF on Canvas along with a blank sheet of this in case it's helpful.
That item count thing, I don't really understand that.
Okay, that's the weirdest part, right? That's a way to capture this information. Think about it like this. This represents a call to the maxval function with an argument of 4. So we're passing an integer. The information that gets returned from this is all of this. It's the actual maximum value, that's an integer. And it's an array of integers that tell us how much of each item we should have in order to get that value of 13. In this case, one of item 3 and no of item 2 or item 1.
An array of integers.
Yeah. So this is a way that we could have, all of this information treated as a single thing, in this case a struct answer. And then we can make an array of those for caching. We can get those back from our maxval and use them to do these other calculations and so on. All right, so let's just take a look at a different example of dynamic programming. This is another classic problem called longest common subsequence. And the idea is, suppose you have 2 strings, like hello. But these strings have other stuff inside them. There's noise, so it could be, A, B, H, X, Y, E, L, Q, 1, 2, 3, Q, L, 25, A, B, O, X, Y, Z. And there's a string H, E, L, L, O contained in here. And maybe I have a second string, which is like, X, 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 H, X, X, A, B, C, Q, 25, E, 25, blah, 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 L, blah, 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 L, blah, 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 O, blah, 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 right? And, inside here is also this string HELLO. And if I analyze these 2 strings correctly, I may discover, hey, there is a string of length 5, right? HELLO, HELLO, that's common to both of these. And maybe there's a longer string that's common to both of them. probably not, because, you know, I did blah, blah, blah. But it's a question sometimes of, hey, given two strings that have, you know, other stuff in between the characters, can we find a common substring between these? Right? Well, you know, here's an AB and here's an AB, and you know, here's an ABE and here's an ABE, and here's an AQ and here's an AQ, right? So trying to pick out strings that are found in both of these, despite other stuff being in between the characters. So a sequence of characters that can be found in both of these, that's called a common subsequence. And the question is, given two strings, how do we find the longest common subsequence between this string and this? And it's hard to do visually. You have to kind of iterate, right? We can start with an A and a B, and we can look for an AB. Then we can look for an ABH, and we can do all of that. And then we can say, let's skip that second character and look for an AH, and an AHX, and so on, or an AHY. And depending on where you start and which characters you skip and which ones you ignore, there's a lot of combinations, right? Now, we could write a bunch of nested loops and do this exhaustively, but for long strings, it becomes intractable pretty quickly. And this is a useful thing to do. It could be useful, for example, when you sequence DNA, because when you take strands of DNA and you break them into base pairs, GATC, you find other stuff in between. There's noise, right? But if I can find a common sequence of base pairs in here that's also in here, I can say, oh, you know, maybe this goes in here, and maybe this is part of a continuation of this strand, and so on. So this is a problem that we could code very easily through a brute force approach, and it would take a really long time to run. But there is a way we can do this recursively, and the recursive vision of this problem is very straightforward, but very time intensive. And so we would take a recursive solution, we would add dynamic programming to it to make it run more quickly. And so here's a recursive version of a longest common subsequence. And these recursive solutions almost always come down to the question of, can I take my problem here and express the solution in terms of smaller problems? Maybe just slightly smaller, but smaller. Now, if I express it in terms of a larger problem, that's not a good approach, because each time that I try to solve that larger problem, I'll have to solve a larger problem, and I'll never finish. But if I can express the solution of this in terms of simpler problems, there's a good chance that I can tackle this with some kind of recursion. So here's the observation we make. We have our string A and our string B. They don't have to be the same length, right? And there's two possibilities. Let's see, is your hand up for a question, or is that an old hand? If you got a question, just interrupt me. Okay. So, okay, no problem. So there's two possibilities, right? Possibility one, suppose that strings A and B end with, you know, the same character. All right, so case one, if A and B end with the same character, well, whatever common subsequence I find between this and this, I know that if I add a Q to the end of that common subsequence, it will be a common sequence between A and B. If I find the word hello inside here and the word hello inside here, subsequence of length 5, I know that I have a common subsequence of length 6, hello Q and hello Q. So if A and B end with the same character, all I have to do is find the longest common subsequence in these truncated strings and add 1. So let me introduce some bizarre notation. A prime means A with the last character removed. So I'm just going to represent a string as A. I'm going to write A prime to say chop off the last character. So if A and B end with the same character, just return 1 plus the longest common subsequence of the truncated strings. Right, so that's one possibility. The other possibility, A and B don't end with the same character. So maybe A looks like this, ends with a Q, and B looks like this, ends with a Z. All right, I know that Q and Z aren't the same character. So if I take the longest common subsequence of this truncated string and this, right, that could also be the longest common subsequence of A and B. Except if that longest common subsequence happens to end with a Q, right, then the sequence I get from here would be too short. But if the longest common subsequence of here and here ends with a Q, that's also going to be the longest common subsequence of these two strings, the original string A and the truncated string B. That takes some thinking about, but the punchline is we only have to return the largest of these two calculations, longest common substring of truncated A and B, or the longest common substring of A and truncated B. And we know that the longest string in common will be either the longest string in common between these two or the longest string in common between those two. And generally, it'll be the longest string in common between those, but it could be that, the substring, longest string between here and here ends with a Z or a Q. So there's a simplified way to look at longest common substring. Again, there's no looping. There's no comparing of things. There's no remembering of where we are and moving forward. It's a very sort of recursive definition. If A and B end with the same character, compare their truncated strings, add 1. If A and B end with different characters, find the longest string between truncated A and B, or A and truncated B, return the largest of those. So it's a recursive solution. Each of these calls will pass in a string that's shorter than the original string. We need a base case. If A or B are empty strings, just return 0. If either one or both of our strings are empty, contain no characters, then there is no subsequence. The longest common subsequence will be 0. And since each of these strings and these recursive calls will, at least one of these strings will be shorter than the original string, we're guaranteed eventually one of our arguments will be a 0, we'll hit our base case, we'll kick out of the recursion. And so we can code this pretty easily. Now C's and string are weird, we know this. So here's my longest common subsequence function. And what I'm doing is, instead of having null terminated strings, I'm passing around pairs of things for each string. I'm passing the array of characters and also its length. And so if I want to truncate a string, I'll just subtract 1 from the length. If I want to know the length of a string, I'll just check the value of its length. So I'm not doing null terminated strings anymore. I'm passing on the strength. So I'll read 2 strings from the user, and I'll get rid of the new lines at the end. and I'll call my longest common subsequence. And for my initial call to LCS, I'll use the string length, because my original strings are null terminated. But inside LCS, I'll just look at this length A and length B. So my base case, if length A is less than or equal to 0, or length B is less than or equal to 0, there are no subsequences, just return a 0. Otherwise, I'll print these out, and I have my own print function, because these strings aren't null terminated. And here's my first recursive case. If the last character of each string is the same, so if the string has length len A, the last character is at index len A minus 1. So if the last characters match, truncate those two strings, just so pass them to LCS, but set the length equal to 1 less than what it is. Get the return value from that, add 1, that's the length of the longest common substring. Otherwise, the last characters differ, so I make two recursive calls to LCS. The first is LCS of truncated B, so A with its original length and B with the truncated length. The second is A with a truncated length and B with its original length, and then I return whichever is larger. And so that's the whole longest common subsequence function. And half of it is just print statements and comments. The actual working code is, you know, a base case, one if statement here, and this could actually just be one statement. And then my print function is just a loop to print out each character, because my strings aren't null terminated anymore. So if I run this, and I'm putting in a print inside LCS so we can see how much work is being done. So if I do LCS and I say, you know, hello and ELO, the longest common substring has a length of 3. I don't know what this will do. I'm probably going to end up with other subsequences that I didn't intend. So there's two strings. I know they have hello inside each of them, but there might be other subsequences too. I don't know if this will finish or not. But you can see that it's making lots of calls to LCS, and you know, here's a call working on A and U, here's a call working on A and U, here's AS and U, here's AS and U. Lots of repeated cases. Now, if I had dynamic programming, this would have finished a long time ago. But every time that I try to calculate LCS of two strings, it has to go through all of these recursive calls. And so dynamic programming will speed this up quite a bit. I don't know if this will ever finish. I'm going to say it'll never finish. So here's the version that has dynamic programming, right? So I have a save array. It's a two-dimensional array because I need an array of strings. And this gets into all kinds of goofiness because it's C, and C is kind of goofy. So this one runs really quickly, and it actually finds the longest common substring. So hey, I got an extra E in there. Cool. And you can see that, you know, the things that it works on are sort of very deliberate, right? It was working on these two original strings, and it kept working on shorter and shorter versions of that second string until it got down to a base case, and then it started truncating that first string until it got down to a base case. And that was that first, you know, recursive call, and it goes on. But it's not repeating any cases, whereas the earlier examples we did without saving our results, right? We kept just sort of going back and repeating the work that we'd done. All right. Well, it was a fast 2 hours. So I may come back and talk about egg dropping, but I think what I want to do first on Wednesday is talk about tree balancing, and then start talking about sorts. Note on quizzes. So there's still some quizzes on Canvas, and they're listed as coming up as due on March 5th. We may not get through everything by March 5th, but they are open until March 11th. So don't worry about turning in those quizzes late. Turn them in by March 11th, which is when they close, which I believe is when the quarter ends. But we may not get to tries before March 5th, for example. So the quiz on tries, you might have to hold off on. But just turn those in before the quarter ends, and you should be fine. All right, that's all I got time for here. Have a good one. I'll see you in 45 minutes if you're in 2:15. Otherwise, I'll see you next time. Thank you.